All right, everyone, good morning. Let's get started with today's exercise. So today we're basically going to see how far we get, but the goal is to potentially finalize the management zone exercise. If you are attending online, make sure you turn on your cameras. So I just launched the project that we started last class. That's the 0-8 management zone. And we stopped here at finding K. So if you recall, let me just do a quick overview of what we've done. So we installed some packages that we're going to need for this exercise. We brought in that layer that we are calling all V, which has all the variables that we processed up until this point, including the yield variables, the terrain variables of elevation, slope, aspect, and flow direction, and also the terrain variable or the EC variables for shallow and deep EC. Also brought in the boundary. We did quickly explore with the summary function. And then we talked a lot about k-means, right? I know some of you were having issues, or maybe all of you were having issues with this. I looked into that, at least on my side. I couldn't really reproduce the issue that you were getting. So I may have to connect with a student here in Athens to understand better what's going on and be able to provide a solution to everyone. So hold on that. You should be able, like, if you at least want to see these figures, you should be able to just copy and paste that address on your browser, and that should pop up the image for you. In case you want to do that way, but the best way would be if you can find the solution and be able to bring that image right here, so you actually can use that as you're reading through the script. Okay, so we talked about k-means, we talked about how it works, how it starts, and how it iterates multiple times until it finds a solution on the center of the clusters. One thing I do want you to remember this, and this may be a fair question on upcoming things, is k-means, you have to tell k-means how many groups or clusters you wanted to look for. If you think of it, the minimum is 1, which is basically the entire data set. The maximum number of clusters is the number of observations in that data set, so it would be 3,600 something. Of course, none of those are what we're looking for, right? So we want a number of clusters where the observations are similar in multiple aspects. So we can create clusters based on that, meaning that we're looking for a solution where K is probably between 2 and 10, let's say, because that would give us between 2 and 10 zones. But still, how do you define if you ask for 2 or 10? How do you know what's the best answer? So that we talked a little bit about that and how we're going to define that. We also talked a little bit about the properties of k-means and also some of its shortcomings. So again, this figure is coming from a paper that had different data sets that we can see here as different rows, and then different clustering algorithms where k-means is the first column here. We just see that k-means does very well when our clusters are circular and compact. It does not do very well when our clusters have odd shapes, or they're not as compact and have outliers. So those are some shortcomings. We're not going to learn any of the other clustering algorithms, but I still wanted you to know that k-means is great and it's very popular, but it's not a silver bullet. Okay, so then we got into this chunk here where we were basically ranking the data to run the k-means algorithm. So k-means does not take NAs, so we have to drop NA first, and it only takes numerical variables. So in this case here, we selected the terrain and EC variables, and we left out the flow direction and aspect. Flow direction because I mean, if you think of it, even though R sees as numerical, but it could have been categorical very easily, by what those numbers mean in that column. And aspect because I think it's one of the columns that doesn't at least doesn't help us as much to understand. And I think it's more really elevation, slope, and EC that were the main drivers when we explored that earlier. So we do that, we wrangle on this node and save this to a new object called allvn. Then we decided we started exploring the k-means algorithm with our data set. We started with 4 clusters, and then we changed to 3, and then we changed to 10. And we saw how much error we were explaining was increasing as we increase k. And that is expected, right? You're giving the algorithm more freedom to create more clusters, and that helps you to explain more of that variability. However, there is a trade-off, right? Again, if you were working with a field that does require 10 zones, then great, go with k equals 10. However, if it's a field that requires maybe only 2 zones and you say that you need 10, then you're just overkilling, right? It's just too much information that you don't really need to manage that field using 10 zones if maybe 2 would have done the job, right? So we want to be just as complex as needed, but not more than that. We talked a little bit about the end start argument and why that's important. I want to say this again, and this also can fairly easily be a question, is what is end start doing, and why do we need to change that to more than 1? It's basically because it's the number of times that k-means runs and tries to find a solution, and because k-means starts off with the center of the clusters, the first step is a random sample of the observations of your data. It means that by random chance, you could end up with all of your centers in one side of the data space, and that could give you erroneous results. So by doing multiple times, you're basically taking away that randomness, or maybe not taking away, but allowing for that randomness to be replicated over time, over multiple runs, and that gives you a more robust answer. Okay, so this is basically where we stopped last class, where we were going to find the best number of clusters for this data. So finding k in this case here. So there are different metrics, actually a lot of different metrics that we can use to define k. I want to show you some of the most common ones here. So the first thing, if you come here on this next chunk, we're going to use this function called fvis nbclust. This function is coming from one of the new packages that we installed for this exercise. So if you load, if you have not done that yet, go ahead and hit the run all above. So you do have all the packages loaded and the data and the wrangle data as well before we start here. So what we're going to do is the first argument that we give this function here is the data coming in. So that is the all_v_n. Remember that allvn is the numerical version that we wrangled specially for k-means. So it does not have any NAs. It does not, and it only has slope. Well, let me print it. It only has elevation, slope, and then EC at 2 depths, and the geometry column as well. We give a comma, hit return, and so it has an argument called method. There are maybe a few different methods that we can specify here. The first one I want to explore is the one called WSS, or within sum of squares. So when we plot it, I'm gonna explain better what this is, and it's gonna be easier when we see the plot. But for now, I guess just knowing it is the within sum of the squares method is probably enough. We have to give it so it has an argument called k.max. So I want k.max to be equals 10. What this means here, it's not the same as end start. This is not end start. K-max is basically telling the algorithm what is the total number of k that I want to try. So it's probably going to go from 1 to 10. So it's going to run the k-means one time with k equals 1, get the result. Run it again with k equals 2, get the result, and so on until 10. And then it's going to provide us that within sum of square data for each one of the case, so we can explore that. And then it also has this argument here called fun cluster. So FUN is uppercase cluster, that we define which function or which algorithm we wanted to test. So we can provide different values here. What we want to provide in this case is k-means, and you don't have to add it's not a function, right? You don't need the parentheses open and closing, just the word k-means does the job. Okay, so let's run this. All right, we got an error here. And unfortunately, the error message is not very intuitive, but I want to tell you what's going on. So it's given us this error because if we look at our data, remember, k-means that cannot have NAs, can only accepts numerical variables. What's happening is that we have this geometry column here, right? K-means doesn't know how to handle that. And I decided not to remove the geometry when we created this object here, because we will actually need that spatial information when we plot the cluster results. So one on-the-fly solution here is if you come to the OVN, you add a pipe. I just want to hit return to break code to make it easier to see. There's a function called st_drop_geometry that I want to use on the fly here. So if I go ahead and only run this piece of the code, what it does is basically what the name implies. It takes that SF object, drops geometry, and that ends up creating just a tibble or a data frame where we still have all the columns except the geometry column. If we do this, that fixes our issue. Or it should at least. Let's try that. It may take a moment to run just because it is running the model multiple times and changing the number of k each time, right? Okay, so this is the output of this metric of the WSS, the within sum of the squares method. So what is this doing? It's plotting us here the total within sum of square for each one of the k's they're ranging from 1 to 10. So the smallest number we see on the total within of sum, the smallest number on the y-axis of the total within sum of the squares, we want a small number here. However, there is a trade-off. Remember, if we just say based on this plot that we're going to go with 10, I mean, maybe that's not the optimal level, because you see the largest gain in explaining variability is from 1 to 2, right? That you can really see that slope is the most steep slope, showing that when you go from one cluster, which is basically the entire data, to 2 clusters, that's when you explain most of the information for this data. And then at each incremental k, we explain a little bit more, but every time you increase k thereafter, you explain less proportionally, right? I mean, you're still explaining a little bit when you're at k going from 1 to 10, but each time that k increases, the amount you're explaining from going to, let's say, 8 to 9 is smaller than the amount that it was when you went from 7 to 8 and so on. So I hope you can see that. The goal here is the k that we would select here would be where we see the elbow in this plot pretty much. So I would say, just visually inspecting this plot, I would say anywhere from 2 to 4 would be a good option for this data, right? Because that's kind of where that elbow is for the most part. And then after 4, we're really gaining less information that may not be, it may not be a good choice, because then we're just creating clusters that are not really explaining a lot more. Okay, so this was the total within sum of the squares method. There are many methods. This is maybe one of the most popular one that people say that they report on papers that they use to define k. Let's try maybe a couple more methods here and see if they even agree. Yeah.
When we try to relate this graph in the practical of the resources in the field, can you say that allocating the management zone Like before we can save the resources, we just have to.
Okay, so Sandesh is asking a question here, and I'm just trying to see if I got his question right. So you're saying if we can relate this result to the resources that we have on the field, what do you mean by resources?
Like any sort of like the model innovation.
So he said resources being like the inputs pretty much. So fertilizer, irrigation. So if you think of it, so here you can kind of think of, I mean, really number of clusters K is really the number of management zones, right? So that's what we're talking about here. We're defining how many management zones we need for this field, which will then relate to inputs, right? To variable rate inputs. But the decision here itself on finding the best number of clusters is not yet defined by the inputs, right? It's more like the workflow is what we're doing as far as getting the data that we know impact crop response, using them to create clusters. So at this point, the clusters that we're creating, remember, are basically only considering terrain and EC data. There is no yield data here. We're going to use yield later to validate the clusters we find, but yield is not part of this yet. And it could have been, I mean, different people use different layers to create zones. Yield could have been a part of it. I decided to not do it, but it's up to the person doing the research to decide that. Or even like if we had other data layers, like if we had a gridded soil sample data where we had nutrients and texture and other things related to soils, those layers could be also part of here, which would definitely change the response of k-means, right? Because now we're given more data so we can learn more about similarities within the variables. But that's a good question. Okay, so this was the within sum of the squares method. The next method we're going to explore is the silhouette width method. It's also a very popular method. I left you almost all the code there. The only thing missing is we have 3 dots. I just want you to delete those 3 dots, so make sure you don't leave them there. And here we're going to say method equals open and close quotation marks S for silhouette width. So if we run this, it's a little bit faster actually. And this is the output that we get from running this method. So it's basically calculating the average silhouette width where we want to have where a higher number is best. So for us, for this data set here, it is already even recommending us to use two clusters because that's where the average silhouette width was the highest. So this is kind of cool. That gives us, a very specific recommendation, whereas on the previous one, it was like, yeah, anywhere from 2 to 4. So it's, this is a little bit more objective. But what if, so there are many metrics, maybe like more than 20. What if you run maybe a few of them and they all give you slightly different answers? One says 2, one says 3, one says 4, and so on. How do you make a decision? So the best way is democracy, is to just run a whole bunch of them and let them vote. And then you basically choose the one, the number of K that has received the most votes. So with that, there is I'm going to run this and then start talking. Do not run this, please, on your side. And the reason for that is because this takes a while to run. You know what? I think I may not even run on my side because it's maybe going to take a few minutes. And I guess we don't need to do that. But on your own, if you're really interested, you can run this algorithm NBClust. So it's basically very similar arguments where we are given the data, we're dropping the geometry, we're just specifying the distance we're using is Euclidean. You don't have to really mind about that for this exercise. We're saying method k-means, we're asking for all indices and telling it to try clusters from 2 to 6. So this basically runs 26 different indices that gives us information about the best number of K. And if you want to do this at home when you have more time and you don't have to be in class like developing code, because this is going to freeze your console for maybe 3 to 5 minutes. So I don't want that to happen in class. But when you're home and you have that time to spare, do run this. and see what happens. So the result of this is gonna tell all the 26 indices, how many voted k equals 1, how many voted k equals 2, and so on, for all the k options that we have. So bless you. So here's going from 2 to 6. I ran this already before, and the result is that 13 of the 26 tests vote k equals 2 as being the best option. And that was the majority. So all the other tests were like maybe 6 tests voted k equals 3 and so on. But the majority vote was 13 tests proposing k equals 2 as being the best option. So this is a way that if you're really, let's say, if you're in grad school, or even if you're undergrad writing a paper and publishing a paper, if you do run k-means for whatever it is, including management zones, and I'm reviewing your paper, I'm gonna ask, how did you define k? If you tell me, oh, I used the silhouette width, I mean, that's an okay answer, but maybe the best answer would have been I tried multiple indices and I chose the one with the most votes. That would be a more robust answer. And I'm showing you how to do that in this chunk here. Again, I'm not going to run this, but when you do run at home, this is the answer you're going to find as well. Yes.
So when you run that top piece of code, it actually, so it just runs the code, and then that bottom, the fviz, MV plus, and that what tells you, gives you that result for you?
Yeah, so I believe that just by running, if I remember well, just by running this, I think it already gives you a written summary. And I think that this function below here just gives you a visualization of that written summary. Yeah, but they get to the same conclusion. Yeah.
So like bucket focus.
Oh, were you able to run? Okay, nice. So maybe it was taking longer on my computer, but yeah. So how many can you just say? Was that 13? Yeah. Yeah. Yeah, so it does provide you the breakdown of how many tests propose different Ks, but the majority one was k equals 2 with 13 votes. Okay, so yes.
So when it's saying all of the different tests it does that just mean it's like doing different ones, like it's doing like silhouette in 12 air and then other ones?
Right. Yeah, that's right. Yeah, and also, something I guess, so every time I show you a function and you're wondering like what is going on behind the scenes, if you have that question, one way to figure out is again to use the help, right? So you can come here and say help and then function name, and it would give you on the documentation, it will tell you about what the arguments mean, and also, so here on the index, there's an index that there's an index argument that we just set all, but you could select specific ones. And if you say all, it just runs all of them, which they're all here. These are what is being run. And if you go on the details, it really tells you what each one of them is, how they're calculated, and so on. So we're not going to get into those details in class, but that's where you would go if you want to know like which indices are being run and what and how they're being calculated.
So that means there are 26 indices. No,
Say that again.
Like it came from like 26 indices. So all
Mhm.
like, 26.
Yeah, 26 indices. Yeah. All right. So based on, I guess, so we, even though we didn't run here, but I'm telling you what the answer would have been if you had run on your side. And when you do run, you will see that. So based on what we're seeing here, the first one, somewhere from 2 to 4 zones. The second one is telling us 2 is the best. And then when we run a lot of them, so 26 indices, 2 is the one with the most votes. With that, I'm pretty confident that we should use 2 zones here, right? So based on those, we make the decision, let's continue our analysis, choosing k equals 2, and therefore having 2 zones only. So we can go ahead on the next chunk. We're gonna pretty much just run that k-means function that we did before. So we do the all vn is the incoming data. We add a pipe and do st_drop_geometry. So it drops the geometry, right? And one thing to notice, I just want to call your attention here that we're doing this we're dropping geometry kind of on the go. We're not saving that to any object, right? So the object that has something saved to it is OVN, which does have a geometry, but we're just dropping that geometry on the go here and not assigning that to an object necessarily. So just wanted to make that clear. So if you add a comma after st drop geometry, we're going to say centers equals 2, right? Again, 2 because k equals 2 was the best option according to the algorithms we ran above. And then just change n start equals to 10 to make sure we run 10 times the same algorithm with 2 centers. So we make sure our final center of the 2 clusters is robust. So we can go ahead and run that. If you run the entire chunk, it already prints for you because I left the code there. And then you can see here, again, we went through a similar or the same output on last class, but it gives you the average on each one of the variables for each one of the clusters, right? So you could really place the center of the cluster if we were to plot, let's say, x being elevation, y being slope, right? You could really see those centers. For us, what we're really after here is this, is the clustering vector, where for each observation in that data set that we provided the algorithm, it gives us a cluster membership that right now is just calling 1 or 2, right? So that's what we're really after, is to get that data out of this. Okay, so what I want to do in the chunk below is to actually do that, use that object that we saved the k-means results to, and create a column in our data that brings in that membership so we can have a column representing the cluster membership, the management zone membership. So if you come here on the next chunk, you're just going to add a pipe, and you can come after this comment here. So after the adding cluster membership, we're going to do a mutate. And I want to call this column cluster. So I want to say cluster equals. Now, a way to bring in that information is to actually call that object. So let me just, so that object, it was called mod KM2, right? So model k-means with 2 clusters. However, if we just do this, it will basically bring all this information here into that column, which it wouldn't even work. So what I really need out of all that information that we get from mod KM2 is just the cluster part of it, the cluster membership. So if we use $, we are going to be able to see that he has a cluster. We can extract the cluster from that object. And if I just run this by itself, I just want to show you, it is a vector with the cluster membership, right? So if we do run this and print it, now we have our original data set. And remember, because OVN itself had the geometry, so the geometry is still here, so we can plot it in space. And now it has this column that is, it says cluster, and its values are either 1 or 2. Yeah, so we can kind of see that. So the way that R is interpreting this column cluster is as numerical, so integer. I do want to change this to categorical because cluster 1 doesn't mean it's less than cluster 2. They're just 2 classes, right? They could have been called AB, high, low, whatever it was. So it doesn't make sense to have them still as numerical. So I want to transform them to categorical. So I'm going to add a pipe here. I'm going to use a mutate. I want to basically overwrite. So I'm using the same column name. And then what function do I need here to transform something from numerical to categorical?
Vector.
Yes. So somebody here now can said, and then I think Sicker. Yeah. Yeah, that's right. So factor, right? We saw that. So that's the function that we use to transform something numerical into a category. So we say factor, and then we just say cluster again, because that's the name of the column. And then we're just overriding this on the same column name. So if you run that and you print it, now cluster is considered as a factor, which is what we wanted. Okay, so now I want to ask for someone else's help here. So this is the data we have, right? If I ask you, I want to know how many observations in our total data set are within each one of the clusters. How can I do that? There may be a couple different ways, but how do we do that?
Tally, cluster.
Can you say that again?
Tally, cluster.
Tally? Is that what you said? So
Yeah.
you just do like and then tally?
Yes. Cluster in the parentheses, yeah.
Let's try that. So that basically is just doing a tally on the entire data set.
Can you find distinct clusters,
We can do what?
distinct, how many are ones, how many are twos?
Okay, so Amrinder saying that we can use the function distinct cluster. Almost, not quite there, but I like the way that you're all thinking. So distinct could have been, but I actually think we need a different function here. So tally is we're gonna need tally there for sure. But what do we need?
Group by and then
Can you say that again, Anis?
we need to do group by first and then tally.
Yes. Yep. So let's do that. If we do a group by and then tally. Oops, I'm missing the pipe here. Yes, that's exactly what we needed, right? So now we created groups by cluster and then we ask how many observations there is within each one of the clusters. So we can see that they're pretty even, right? I mean, they're pretty close in number of observations. That doesn't necessarily have to be the case. Sometimes you could have a cluster that controls most of the points and then a smaller cluster as well. But this is how many observations it turned out to be for this data, right? So yes, thanks everyone for help. Okay, so as usual, and if you've been following closely what we've been doing, every time I create a result, I like to plot it so we can confirm what's going on. We can see where these clusters are. We can really have a map of these clusters in space. So we know, like, are they pretty contiguous or are they all mixed? Like, how do they look in space, right? So let's create a map here. And I do want to have a map of the clusters to color by cluster, right? So as I'm telling you these words, I hope that you're already thinking of what types of functions we need to do that. So the data set that we're going to start off is zone DF. Let's add a pipe and call it ggplot. Which function, let me ask someone else, which function do we need to plot a map of the clusters? We're using this object here, right? So just for your reference, again, zone DF is an SF object. What function do we need here, Alexis? GeoMap. I don't know if that is an option. Well, it is. I never use it, so I don't know what it does, but so maybe it would work, but for the sake of not trying different things on the fly, let's just think of what we used in the past. What do you think, Bo?
GeoMSF.
Yes, that's right. GeoMSF. Thanks, Bo. So I do want to have here. Well, let's just run this and see, right? Okay, so we have our SF polygons for each one of the pixels, but I do want to color this by cluster. What do we need to change in this code to make that happen? What do you think, Peter? Yes. So AS. So in this case, well, we can do what you said. So you said color equals cluster. Oops. Cluster. We can do that, and I do want to show you what happens when we do that. right? So if we could do cluster, but I think fill is gonna be better, right? Because color is the outline in this case, and we do want the fill to be equals cluster, which looks like this, is a little bit more clear. And I do want to remove that black outline of the clusters. So I get outside of the AS and I say color equals NA. Just so we make it like easier for us to see the clusters. Okay, so we can see that the clusters, for the most part, they're pretty cohesive, right? We have a cluster on the left side, a cluster on the right side. I do want to call your attention to the following. Because of the randomness of the first step of k-means, it is possible that you have cluster one, so your colors may be flipped, as what I'm trying to say. Because for me, cluster one is on the east and two is on the west. It could have been the opposite. So if you're seeing the opposite, that's completely okay. And it is because of that randomness aspect of the first step of k-means. Even if I rerun this on my side, maybe another time, I may get them flipped. What will not be flipped is the answers. I mean, even though the names 1 and 2 may change, but the assignment, the way they look in space should not change. So just wanted to make that point. So at this moment, if you have the colors flipped, don't worry, we're going to address that later. Okay, so just looking at this, we do see that for the most part, they're pretty cohesive clusters or management zones. We do have some intrusions or whatever that would be called, right? So we do see a little bit of at least of cluster 2 inside cluster 1 right there. We do see some specks of cluster 1 inside cluster 2. And this raises a point that I think is worth to talk about it here, but also for you to keep in your mind when you do this type of work, even if you're not using R, if you're using whatever other software, always is a good conversation is this the final map as far as these are my management zones, let's move forward with this. Or maybe should we try to address these specs of different clusters inside the larger ones? So this, comes back to first the cell size. If you recall, our cell size is 10 by 10 meters, so that's about 30 by 30 feet. Is that cell size something that a producer can manage at that level? That let's say, if you think of like this one red cell inside of a blue ocean here, is that something that this producer will have the capacity to, like, applying a fixed rate or applying a given rate on cluster number 2 on the blue, and then change that just for 1 pixel and then change it back to blue? I don't know, maybe not. And is it even worth the trouble, right? I mean, if it is such a small cell surrounded by cells that are different, is it even worth the trouble of having the machinery change rates for such a small part of the field just to address that? I personally think it's not worth it. I think, it would be better, especially the way that these clusters look like this way. We have large clusters and then some small areas where we have these specks of different cluster inside the larger cluster. So in my opinion, I think we should not have these small specks here. So these small red ones that are by themselves, and maybe even something about those blue ones inside of the red one. Let me just see here. Oh, so I do have some more code here for us to finalize this plot. Even though this is like the backbone we needed for the conversation, I do want to further develop this because we're going to need to do some things about it upcoming. So let's just finalize make this plot nicer. So add a plus there. I do want to change the scale of the fill. So scale underscore fill underscore. I want to use a different one today. So it's called colorblind. It's still colorblind safe, but it's not for Redis. So if you run it, you should get black and orange colors at this point. I do want to bring the boundary. So that would be geom underscore SF because the boundary is an SF object. We have to say data equals in the object that we save the boundary. We imported that in one of the first chunks. It's called boundary W. And if, I'm gonna run this so you can see, you should be already expecting to not be able to see through. And we fix that by using fill equals NA. So we see the boundary, but we can also see through it. I do want to change, I want to give this map a title. How do we do that? Maybe that's a somewhat newer thing. We've seen already in the past, but how do we add a title to this map? Or to really any ggplot, not just a map?
Is that the labs function?
Yes, that's the labs function. That inside of it, if you hit tab, it shows you all the options there. There is one option that is title. And then we can say, I want to give a title that is called unsmoothed zones. And was who said that?
Ethan?
Okay, thanks, Ethan. Yeah, so if we do that and we run it, we do get a title now. I do want to change the theme, so I want to add a plus, and we're going to use theme underscore map to remove the axis and make it just cleaner overall. And lastly, I want to do something that maybe we haven't seen in class, but I know some of you have already explored on your own, especially on the mini project. I want to change the color of this title to blue. So for that, changing an appearance component of the plot that is not related to variables, is not related to a geom, normally will be within the theme function. So we add a plus, we come here and we use theme. And here there is, if you hit tab inside a theme, there is a whole bunch of options. The one I'm looking for is plot dot title. Because plot title is an element of type text, and I guess there's nowhere that you can check that. It's more, a guess. We have to say element text function, and then inside here, we say color equals blue. If we were changing, for example, the legend in itself, depends on what we change about the legend. But if we think of like, oh, I want to change the box of the legend to be something different, to maybe have like an outline, or maybe make that outline blue in this case, I guess it would be a good example as well. We would be using element rect for rectangle, because it is a rectangle that you're trying to change, is the box of the legend. So just so you have a little bit more of like, why are we using element text here, and when would that not be the right option? So if you run this, this is how it looks like. And this is what I'm pretty happy with this. I do want to export this to file. How do I save a plot to file? David, what do you think? What function do we need to save this plot to file? Yes, dgsave, thanks. So we use dgsave. We're going to give it, the first thing we do is give a path. So we open and close quotation marks. So we need to get outside of the code folder that requires .. If we hit tab, we are on the main folder of this project. We want to go inside output, and then we give the name and extension of the file type. I want to call this zones.png. You get outside of the quotation mark, add a comma, and I just want to change the width. So I want to make width equals 3 and height equals 4. And I believe these are in inches. So if you run that, and then you come on your Files tab, R button, output, you should see now that zones right there. Okay. So I think we can stop about here today. I just want to tell you that the immediate next step, let me just print this map again so we can see. The immediate next step we're gonna do on Monday, and I believe we're probably gonna be able to finish it, is to first thing is smooth the zones. By smooth, I mean basically remove these points that are loners, I guess. Intruders of one cluster inside the other, and just make this a smooth map overall. We're gonna use a focal operation to do that. I guess for today, we can pretty much stop right there, and I don't want to, get a lot more information to you to not confuse you, but that's what we're gonna be doing next. And just as a heads up, there's gonna be an assignment about that at the end of next class. So we do expect an assignment coming about this. But for today, I think we can stop here. So I'm gonna save here. I want to open a GitHub issue for attendance. Okay, so please go ahead and claim your attendance if you're watching live. And this is all for today. If you have any questions, I'll be here for a couple more minutes, and if not, feel free to disconnect or to go to your next activity.